easy to read because they are quite some difficult theory, but take a look, see what. But before we go forward, right, let's just review the subthreshold slope again, right? Can someone tell me what is subthreshold slope?
It's the change of voltage on the gate to get an increase in current of 10 times.
Yeah, very good, right? So I assume you all know this. So now I'm not going to write it down, okay? But now what we care is, and based what you said, it is like this. The change of gate voltage for every 1 decade change of the current. That is basically what you have said. Because for 1 unit of the denominator is just like 1 decade, right? I take the log scale of the drain current, right? If you go from 1e minus 8 to 1e minus 9, that is difference is 1. That's why partial. And then how much gate voltage I need to put, right? Now let's look at this again. For every device, we have an insulator, right? I showed you before. And then you have the substrate. This one can be the depletion capacitance, right? But we lump them together because there may be fringing capacitance, right? Your transistor is not perfect. You don't only just have the vertical depletion capacitance. And also when your drain bias is high, it is not uniform. So let's just call it CS. If you look at this device, you see partial VG can be represented as partial psi S, partial psi S, partial log 10 ID. Some of you may say, hey, you taught me this before. We did that before. This is just a review. Okay. Now, what is the relationship between psi S and log 10 ID? Psi S is the surface potential, right? We're talking about this one. This is psi S. This is source. This is drain. And then you have this capacitor, Cox, connect to VG. But this psi S further connect to 0 through CS. Right? Remember this? And because of this, we don't get the perfect one, right? But if we can change psi S directly, we get the perfect one. What is the perfect value for partial psi S, partial log 10 ID? Do you remember?
One.
They are different unit. One is volt, right? And other is current, log current. One, you're right. Your concept is correct. You're trying to say 100% of the action of psi S change convert to the ID change. But now it's talking about partial psi S, partial log 10 ID. What is that at the room temperature? Why do you say 1? That is the main point.
To get a better subthreshold slope, that's why I said 1, so that it will get the full 60 millivolts per decade.
Exactly. So the value is actually 60 millivolt per decade, right? What you mean 1 is 60 millivolt per decade. Or it is KT over Q natural log 10. This is this part. Okay? How about psi G, partial G, partial psi S? Do you still remember? This is the capacitance divider. Okay? Maybe you forgot. Just 1 plus CD divided by, in this case is CS, divided by the insulator, C-ins. Right? Remember that is in the midterm, right? Then I asked you how you can improve it. Some of you say have a smaller depletion width, CS smaller. or increase the control by increasing the gate capacitance. Any question about this? Even you forgot the equation, you must memorize this. I hope that you memorize. Transistor is just a switch. Our goal is to change the current based on the gate voltage. But the current doesn't listen to you completely. It's just like this is the employee, the current. The current actually listens directly to the manager. And then you are the VP. You say something, you say, you guys work from 9 to 5. When it comes to the manager, somehow it becomes from 10 to 5. Okay? And then the current only work from 10 to 5, the employee. You lose some control. Why is that? Because first we need to transfer the change of the gate voltage to the change of the surface potential. They are not directly in touch with each other through this capacitor actually. But then you have capacitor divider effect, just like resistor divider effect. So I change VG by 100 at 60 millivolt, 100 millivolt maybe. Vs may only change by 60 millivolt. Okay? And then this Vs really has a complete control on this current. Theoretically, it's KT over Q log 10, right? So you need to memorize that about this capacitor divider effect. And the whole device physics, main part of this nowadays is about how can I increase the control? One of that, get rid of the manager. Let the VP control the employee directly. Yeah. Do you know if I get rid of this capacitor, what type of device it becomes? When I don't have this resistor, I have the gate, I have the contact, touch the body directly. What type of device is that?
Wouldn't it be like a
MOSFET?
no, not
Empt?
no, I'm thinking of like the bipolar junction because you have a NP and an N if it's an NMOS.
Correct. That is the BJT. For BJT, if you don't have other non-ideality, you get 60 millivolt per decade. Bipolar junction device. Someone just say MOSFET. That is also correct. But when you say MOSFET, you actually form a Schottky contact. So you still have a capacitor here. It's not as good as the BJT. BJT is an ohmic contact. Okay, so both of you are right. But what I'm fishing for is for BJT. Right? We can do that. But then you have a lot of leakage current. Right? That's why we stop BJT and come to MOSFET. Right? So this capacitor is something hurting us. So there are two things. How can I increase the subthreshold slope? Well, maybe I can increase the subthreshold slope by changing KT over Q. Change this physics. You can change the equation. No longer KT over Q. That we will discuss later. For example, tunnel FET, tunnel field effect transistor. It does not obey KT over Q because the transport does not depend on fermionic emission. Okay? Or you say, I am rich. Let me just put in refrigerator, make it at very low temperature. You still rely on fermionic emission, but now you make the temperature low, so you get higher subthreshold slope, which is also okay. Now, but you may say, well, why don't I just reduce this? Right? Can I make this one small? For example, let me make CIS very large capacitance. Or let me make this one very small. Then what will happen? This is so-called N, right? N becomes what? When the CIN is very large.
1.
0.
1.
I mean 1.
1, right? But then overall is still how much? 60 millivolt per decade. What do you do here when 1? We did that already. We use double gates. right? We use SOI, we use FinFET, we use all these traditional things. We try to make it one actually by increasing the gate control, by reducing the depletion capacitance. But we are not happy with that, right? For all of you, I think, can you tell me, can I make it smaller? Can I make the N even smaller? If I can make it smaller, let's say 0.1, then I can get 6 millivolt per decade at room temperature. Can I make it smaller? And this is the time you need to brainstorm and really not to be confined by what you have learned since you grow up. And because if you can break the box, then you will be a very successful people. Can someone tell me how I can make it less than 1?
Make the capacitance negative.
Make the capacitance negative, right? No one dare to say that, right? If before people really found out, right? If you tell your EE introductory class teacher, should I have a negative capacitance? That depends, right? They will say that is impossible or whatever, right? No, actually, probably it's possible. They know already for other circuits, right? If you don't talk about ferroelectric, we can make it negative. It's almost impossible to make CS negative because this is the transistor, but let's make this one smaller than 0. So in that case, N will be smaller than 1. And that is what we want. We try to obtain partial G, partial psi S to be less than 1. Sorry, I typed the right thing, right? CINS, right? Any questions so far, right? So the main point is I hope you have these insights about transistor, how it controls the current. It is a 2-step from VP to manager, manager to staff. Somehow the manager always take commission. So your command cannot go to the staff. So you have 2 ways, either change the manager. This is this one. Or do something strange. You can boost the manager, right? When you ask manager to deliver 10 units of product, somehow he's so scared of you, he will try to target for 12 units. Any questions?
So this is even better than using the fully depleted SOI.
Yes, because fully depleted SOI only give you 6, if you do it very well, only 60 millivolt per decade. This one, I can go to below 60 millivolt per decade. If you're interested, after this class, just Google, type sub 60 millivolt per decade. It pop up tons of paper talking about how they get sub 60 millivolt per decade. And if also type negative capacitance, then it will be all about the experiment and simulation for this sub 60 millivolt per decade using ferroelectric device. Okay. I spend a lot of time, but I really think this is an important concept, right? I would rather if you forget everything in this class, but really imprint in your brain that you have this 2 stage. And actually mentioned before, but at that time you won't appreciate so much. Now we go to negative capacitance ferroelectric material, then this becomes important. So the goal of this class is very simple. How do we make negative capacitance? Okay. So first of thing, we try to talk about what if we can create a system that has a positive feedback. Right? So let's try to just have an understanding. Let's say I have a capacitor. That's what I try to make it negative, right? CINS. I say, what if this capacitor is modeled as this one, right? We try to model. Let's say I just have a regular capacitor, okay? And this happened in circuits already. and I apply a voltage, which is V1, okay? But interestingly, I have a charge control voltage source here. It delivers negative alpha Q. Q is the charge that I deposit on top of the capacitor. This is possible. You can build a circuit to do that. So actually, negative capacitance concept is everywhere, even in undergraduate class, right? We are going to see negative capacitance when we have this feedback. So this is just a model, right? Just to tell you that, hey, if you have some positive feedback mechanism, it is possible to get negative capacitance. Let's try to look at this circuit. First of all, what is a capacitance? CINS is just equal to what? Q divided by V, correct? And here is V1 minus 0, right? As the whole circuit, right? I don't tell you this is so complicated. I just say measure the capacitance of this system. You apply a voltage V1 across it, and then you measure how much charge is deposited there. That gives you the capacitance by definition, right? Now, then let's try to study. What is Q actually? Q is just the charge across this C0. So it is just the voltage, C0 times the voltage across it, V1 minus negative alpha Q. This is just the voltage across C0, correct? The top is V1, the bottom is negative alpha Q, right? And divide this by V1. So this one gives me C0 V1 plus alpha Q divided by V1. Okay, so let's try to find out what is the effective capacitance now. This is V1. I'm a little bit lost, sorry for that. Yeah, so I'm a little bit lost in my derivation, but that is okay. Now, actually, I need to go back. You see that from here, I showed that Q equal to C0 V1 minus alpha Q, right? Here, this one I already told you Q equals to C0 V1 minus alpha Q. So I want to take out the Q first before I put in CINS. Okay, so this one gives me what? This one gives me Q. I just move the right term to the left, equals to C0 V1 divided by 1 plus alpha C0. Sorry, this is a plus, right, instead of negative. So this is negative. Is this okay? Q is here. This is C0 V1 plus alpha Q, right? Then I move this term to here. On the right, I keep C0 V1, and then this one move to here becomes 1 minus alpha C0. Okay, now then I substitute this one back against C in equal to Q over V1. So now I substitute this into here. The effective capacitance is this one, right? I substitute this Q to here and divided by V1, so V1 got canceled, right? So if 1 is smaller than alpha C0, what do you get? You get CINS smaller than 0, which is a negative capacitance. Is this okay? Sorry if there's a glitch in the derivation, right? But the result is still correct. All I want to tell you that if you have a positive feedback mechanism, here is a positive feedback mechanism. It causes negative capacitance. With positive feedback mechanism, I can make a negative capacitance as a whole. So there is no magic. You see, there's no magic, right? You were still correct. Capacitance has to be positive. But it's just that the effective capacitance can be negative. If we have a little demon sitting inside the dielectric, want to play game with you, instead of doing the regular polarization, it swap it, then you feel that this is a negative capacitance. And nowadays, we have a lot of this type of physical phenomenon being used in solid state and for the future device. Okay, any questions about this? But however, this is not stable. You cannot do this in experiment, right? Think of this. If Q increase, let's say I increase the Q a little bit. What happened to negative alpha Q, right? It's more negative, right? So for example, you have a 1 coulomb. This becomes maybe more negative 10 volt. And when this is more negative 10 volt, then the V1 minus alpha Q become larger, right? More positive. So if this is more positive, the Q will continue to increase, right? The voltage across the CO is larger now. Then I have even more charge. So this is a positive feedback. It is not stable. It is not stable. And eventually it will run into second order distortion, nonlinearity. Then you cannot use this equation anymore. It's just like the amplifier. It's just stuck at the rail. You don't get any useful negative capacitance. Okay. So how do we make it stable? We need to have positive capacitance after connected to external capacitance and other capacitance. Okay, so this one is not stable. Okay, so we show that we can do it, but it's not stable. You cannot do it experimentally. Is that okay? Any questions? Any question about the source of the negative capacitance? It is indeed a positive feedback in ferroelectric material. This is just a model. Now, then how can I make it stabilize? Okay, this figure, we look at the figure later, right? The point is that to make it stabilize, you need to make the total capacitance positive, which means you need to make C-ins parallel CS larger than 0. So it's okay if you have a negative C-ins. Okay, I'm saying that it is okay if you say that you have this one smaller than 0. But for your system, C-ins and this CS, when they're in parallel, they are in parallel indeed, right? They have to be positive. If they are negative, it won't work. Okay, right? Just take it for granted, right? I don't know if I really understand also, right? This go to thermodynamics and other things, right? But just take it for granted. They are when they're parallel, they have to be larger than 0. And what is that? It means C-ins CS divided by C ins. CS has to be plus CS, right? This is when they are in parallel, has to be larger than 0. Okay, to be stable. And once it is stable, then it is possible for this negative capacitance to come out. So what are the possibilities that I can make this larger than 0 for negative CINS, right? If Cins larger than 0, then of course stable, right? But what if Cins smaller than 0? How can I make this stable? One possibility is to have Cins, the absolute value, larger than Cs. When this is large, both the denominator and numerator will be negative. So it is larger than 0. And I still have the negative capacitance here. Is this okay? Now, then what I mean by stability, right? This one I really can just say it. It's very difficult to explain unless we write a chapter, write a paragraph about this. This is a kind of ferroelectric material. X-axis show the electric field. Y-axis show the polarization. Now you understand what is polarization, right? Basically, I have an ferroelectric material. It's not difficult to understand. If I have an electric field here, the net electric field, what do you expect? I expect negative charge here, positive charge here, polarization pointing in this direction. So is that right? Well, we'll start from 0. When you start to increase the electric field, right? Polarization pointing in the same direction, isn't that? Same as what we learned. So you keep going. Eventually, it's saturated. It doesn't increase too much. Polarization saturated. Now I try to reduce the electric field and come back. And guess what? It will follow this one. It doesn't go back to original curve. That is because the molecular structure for this material, for the electric material, is just like an interlock. We'll look at that later. Once you bend it the other way, it's just like a plastic, you know, a little bit bulge in this direction. Once you bulge to this direction, when you want to go to another direction, you need to press more than it is, than 0. Right? Originally, you think that if I put negative force in this direction, I hope that it will come down. But it doesn't, because it just get locked there. When my force is large enough, then you will suddenly go top, flip to another direction. And this is like what it is doing here. When I force electric field becomes 0, it is still polarizing in this way. Even now, I don't have electric field. It's polarized. So I need to keep increasing the electric field until it is so negative. Then it will suddenly flip to another way, just due to the molecular structure. Now polarization will go to the negative side, and it suddenly go all the way to negative. Using the same token, you see that when you're going back, you also have this thing. That's called hysteresis. This is a very useful stuff you can use as a memory. So people study ferroelectric material at the beginning actually for memory, just by stable. Once it shifts to here, then polarization is here. I can distinguish from another state easily. So here you don't see any negative capacitance, because by definition, capacitance is dq dV, and here it's just like dP dE. Because they are just the scale version. The Q and P is just conjugate to each other. V and E is just different by the thickness, right? If you want, you can multiply this by T. So you see that everything is positive. All the slope means this is the slope, right? The slope is positive. So in reality, just think about this physics. You cannot get negative capacitance, okay? But however, if you bias it correctly, this structure can behave using this curve instead of these two curves. And this is a negative slope. And this is where you get negative capacitance. Okay, but how do we get this? Not very clear. I'm going to keep telling you, like mention more, but at this point, it's not clear. But I hope that you understand that negative capacitance, you cannot get negative capacitance by just using the ferroelectric material. You need to be in parallel with another capacitor. And due to all the dynamics and positive feedback inside, and if you can do this with the CINS value larger than CS, then it's possible to let this field to switch in this direction to get the negative capacitance. Okay, any questions? So here is just a repeat of what I told you. Usually this is called perovskite material. It has an oxide